Hi, I'm Adrian Nagtalaw, and this is my presentation for angular modulation, frequency modulation, and phase modulation. Frequency modulation. Frequency modulation is a modulation in which the frequency of the carrier wave changes according to the instantaneous amplitude of the modulating signal, keeping phase and amplitude constant. The frequency of the carrier wave is modified in order to send the data or information. It cannot transmit over long distances, have a smaller range. Its modulation index is always greater than 1. In frequency modulation, amplitude and phase remain the same. Phase modulation. Phase modulation is a modulation in which the phase of the carrier wave changes according to the instantaneous amplitude of the modulating signal, keeping amplitude and frequency constant. Phase modulation and frequency modulation are similar, but in phase modulation, frequency of the carrier signal is not increased. Phase modulation is used in mobile system. The phase of the carrier wave is modified in order to send the data or information. Difference between frequency modulation and phase modulation. Here is the comparison between the two. In frequency modulation, amplitude and phase remain the same. In phase modulation, the frequency and the amplitude remain the same. Frequency modulation is proportional to modulating voltage. Phase modulation is proportional to modulating voltage. Associated with the change in frequency, there is some phase change. For phase modulation associated with the change in phase, there is some frequency change. It is possible to receive frequency modulation on a phase modulation receiver. It is possible to receive phase modulation on an FM receiver. Noise immunity is better than AM but worse than PM. Noise immunity is better than AM but worse than PM. That is for both frequency modulation and phase modulation. For frequency modulation, signal to noise ratio is better than in phase modulation. For phase modulation, signal to noise ratio is poorer than frequency modulation. Frequency modulation is widely used. Phase modulation is used in mobile system. The frequency derivation is proportional to the modulating voltage only. The frequency derivation is proportional to the modulating voltage as well as modulating frequency for phase modulation. Amplitude of FM wave is constant. Amplitude of PM wave is also constant. For frequency modulation, received signal is of high quality. Compared to phase modulation, received signal is of low quality. Frequency modulation time domain. Frequency modulation time domain. This is the graph for 10 MHz carrier. The base band signal will be a 1 MHz sine wave as follows in figure 1.1. The FM waveform is generated by applying the formula given. Thus, the integral of sine of x is cosine x plus c. The constant c is not relevant here, so we can use the following equation to compute the FM signal. X sub FM sine 10 times 10 to the 6th times 2 pi t minus cosine 1 times 10 raised to the 6 times 2 pi t. Frequency modulation time domain. Here is the result. The baseband signal is shown in the end in figure 1.2. It almost seems that the carrier hasn't changed, but if you look closely, the peaks are slightly closer together when the baseband signal is near its maximum value. So we do have frequency modulation here. The problem is that the baseband variation are not producing enough carrier frequency variation. We can easily remedy this situation by increasing the modulation index at m is equal to 4. X sub fm is equal to sine 10 times 10 raised to the 6th 2 pi t minus 4 cosine 1 times 10 to the 6 times 2 pi t. Now, we can see in figure 1.3 more clearly how the frequency of the modulated carrier continuously tracks the instantaneous baseband value. Phase modulation time domain. We'll use the same waveforms that we used for the FM discussion. The 10 mHz carrier in figure 2.0 and the 1 mHz sinusoidal baseband signal in figure 2.1. Here is the FM waveform with m is equal to 4 that we saw in figure 1.2. We can compute the PM waveform by using the following equation where the signal added to the argument of the carrier wave uses positive sign instead of the negative cosine. X sub PM is equal to sine 10 times 10 raised to the 6th times 2 pi t plus sine 1 times 10 raised to the 6th times 2 pi t. Here is the phase modulation time domain, phase modulation time versus amplitude, the PM plot, figure 2.2. Before we discuss this, let's look also at a plot that shows the FM waveform and the PM waveform in figure 2.3. The first thing that comes to mind here is that from a visual standpoint, FM is more intuitive than PM. There is a clear visual connection between the higher and lower frequency section of the modulated waveform and the higher and lower baseband values. With PM, the relationship between the baseband waveform and behavior of the carrier is perhaps not immediately apparent. However, after a bit of inspection, we can see that the PM carrier frequency corresponds to the slope of the baseband waveform. The highest frequency section occurs during the steepest positive slope of x sub bb, and the lowest frequency section occurs during the steepest negative slope. This makes sense. Recall that the frequency as function of time is the derivative of phase as function of time. With phase modulation, the slope of the baseband signals governs how quickly the phase changes. The rate at which the phase changes is equivalent to frequency. So in PM waveform, high baseband slope corresponds to high frequency and low baseband slopes corresponds to low frequency. With frequency modulation, we use the integral of x sub bb, which has the effect of shifting the high frequency carrier section to the baseband values following the high slope portions of the baseband waveform. Modulation index. Modulation index m is equal to frequency deviation over modulation frequency. To give an example of the FM modulation index, take the example where a signal has a deviation of plus or minus 5 kHz and the modulation frequency is 1 kHz. then the modulation index for this particular instance is 5/1, which is equal to 5. Percentage modulation. The FCC's rule and regulation limit FM broadcast band transmitters to a maximum frequency deviation of positive 75 kHz. The maximum allowable deviation will be assigned the value of 100% modulation. Therefore, in equation form, the percentage of the modulation is given by percent modulation, sigma over sigma max times 100. This parameter is normally displayed at FM radio transmission station when the signal is aired. Frequency deviation. A sinusoidal modulating waveform of amplitude 5 volts and frequency of 2 kHz is applied to FM generator, which has a frequency sensitivity of 40 Hz per volt. Calculate the frequency deviation. So for the solution, with the given amplitude of the modulating signal AM is equal to 5 volts. Frequency of the modulating signal is FM 2 kHz. Frequency sensitivity KF is equal to 40 Hz per volt. We know that the formula for the frequency deviation is delta F is equal to KF AM. Substitute KF and AM values in the above formula. Then we will have the frequency deviation 40 times 5. We will have frequency deviation equal to 200 Hz. Frequency deviation. If the phase modulation is performed using the message signal 10 cos 2 pi times 10 raised to 40 used in the previous slide, find the phase deviation constant Kp giving the PM signal the same bandwidth, namely 120 kHz. Solution. For both the FM and PM signals to have the same bandwidth, beta and delta F must be the same. For FM, delta omega is equal to KF AM, but for PM, delta omega is equal to Kp M prime P. Expressing the message signal M of T is equal to AM cosine omega M T gives M prime of T d over dt AM cosine omega M T is equal to negative of omega M AM sine omega M T. M prime P is equal to negative omega M AM. Thus, KF AM is equal to the negative KP omega M AM. Kp is equal to Kf over omega M, which is equal to 10 to the 4th pi over 2 pi times 10 raised to 4. Simplifying, we will have 1/2. Deviation ratio. D is equal to delta F over W. M is equal to max frequency deviation over max modulation frequency. One common example of the FM deviation ratio can be seen by taking the figures of a typical FM broadcast station. For these stations, the maximum frequency deviation is positive negative 75 kHz, and the maximum audio frequency for the modulation is 15 kHz. Using the formula above, this means that the deviation ratio is 75 over 15, which is equal to 5. Bandwidth. FM signal spectrum is quite complex and will have an infinite number of sidebands as shown in the figure. This figure gives an idea how the spectrum expands as the modulation index increases. Sidebands are separated from the carrier by Fc plus or minus Fm, Fc plus or minus 2 Fm, Fc plus or minus 3 Fm, and so on. Only the first few sidebands will contain the major share of the power, 98% of the total power. Therefore, only these few bands are considered to be significant sidebands. As a rule of thumb, often termed as Carson's rule, 98% of the signal power in FM is contained within a bandwidth equal to the deviation frequency, plus the modulation frequency doubled. Carson's rule, bandwidth of FM, BWFM, is equal to 2 delta F plus FM is equal to 2FM MF plus 1. The frequency modulation is known as the constant bandwidth system, and an example of this is this system is given. Bandwidth is equal to 2D plus 1 W or 2B plus 1 FM, F sub M. So delta F is equal to 75 kilohertz, FM is equal to 500 hertz, bandwidth for FM is equal to 275 plus the quantity of 500 over 1000 kilohertz, and that is equal to 151 kilohertz. Delta F is equal to 75 kilohertz, FM is equal to 5000 hertz, BWFM is equal to 2 times the quantity of 75 plus 5000 over 1000 kilohertz, and that is equal to 160 kilohertz. And lastly, delta F is equal to 75 kilohertz when the FM is equal to 10,000 hertz, BWFM is equal to 275 plus 10,000 over 1000 kilohertz, and that is equal to 170 kilohertz. Although modulating frequency increased 20 times, 50 hertz to 5000 hertz, deviation increased only marginally, 151 kilohertz to 170 kilohertz. Hence, FM is known as a constant bandwidth system. Commercial FM or Carson's rule. Max frequency is equal to 75 kilohertz. Max modulating frequency is equal to 15 kilohertz. BWFM is equal to 2 times 75 times the quantity of 75 plus 15, which would total 180 kilohertz. Here are the references that is used for this presentation. That would be all. Thank you.